presenter, Deepak Cherian. So Deepak is a Forwaed Engineer here at Earthmover, and an accomplished physical oceanographer and open source developer. So Deepak has a PhD from the MIT Woods Hole Joint Program in Oceanography. He spent some time as a postdoc at Woods Hole and Oregon State before accepting a position at NCAR, where he worked prior to this for the past 4 years or so. In addition to his work on ocean turbulence, Deepak has become a really prolific contributor to the Pangeo open source software ecosystem as a core developer of Xarray, the creator of the Flux package, CFXarray, and a lot of other tools in this space that we've all come to rely on deeply. And so Deepak is one of those rare individuals who has a deep mastery of both the scientific applications and the full software stack that we use to do research and data analytics. So really excited for Deepak's presentation today. And thanks to all of you for coming out. I'll turn it over to Deepak. Take it away.
Great. Thanks for that nice introduction, Ryan. And thank you for all of you. Thank you to all of you for joining us today. I'm going to talk about building analysis-ready forecast data cubes with Zarr. And so first, some housekeeping. Please remain on mute unless you're actively asking a question. You should be able to submit questions through the using the Q&A functionality that you should see at the bottom right of your screen. At the end of the session, if you have time for questions, please use the hand raise feature to ask that. At Earthmover, our mission is to empower people to use scientific data to solve humanity's greatest challenges. And to do that, we've assembled a team of accomplished scientists, open source community leaders, and very experienced engineers who come from many big private sector companies. We have a lot of experience in our founding team. Ryan and Joe both come from deep scientific background and have worked at large research institutions previously. And the rest of us on the team also come from research backgrounds as well as, and have worked building production-grade pipelines at many private sector companies. We also come to this endeavor with a strong foundation in open source communities, in particular the Pangeo community and associated packages like Xarray, Zarr, and Dask. And so as Ryan mentioned, my name is Deepak Cherian. Today I'm a Forwaed Engineer at Earthmover. I come with a strong background in physical oceanography and have worked at a number of oceanography and climate research institutions in the past. Through my research work, it became very clear to me that the ability to handle and analyze the increasingly large data sets in Earth system science were a real rate limiter for scientific progress. And I saw a lot of my colleagues struggling with how to do this. And so over the good chunk of the last decade, I've spent working in open source scientific Python community, trying to just make that experience a lot easier, particularly through Xarray, where I'm now a maintainer, and various related packages in the Pangeo ecosystem. So today I'm at Earthmover to kind of devote my time 100% at solving those challenges. And so at Earthmover, we are trying to build a product that is very complementary to our open source layers. So the two packages in particular that we help maintain and build are Xarray, which if you haven't heard of it, is pretty great. It lets you use your metadata to analyze, help express your analysis on large n-dimensional arrays and datasets in Python. It uses the metadata associated with those arrays to help power a nice API that lets you select, compute, and visualize those data sets. And so that we think of that as a kind of compute interface. The storage interface that we build on is Zarr, which is a cloud-native data format for chunked and compressed n-dimensional array data that is very typical for Earth system science. And it's got wide compatibility with all cloud object stores. And so on that note, later today, this afternoon, our CTO, Joe Heyman, is going to be speaking about the next evolution of Zarr. So the title is Zarr v3 and why you should be excited. I already know what's coming and I'm pretty excited. So shout out, you should go see that later today if you have the time. If not, it'll be recorded. So the product we're building is Array Lake. And like I said, it's complementary to these open source layers. The way we think of this is as follows. So in your group, research group or organization, you probably have a bunch of people working on interactive notebooks workloads, they're developing machine learning models, they're probably running large batch compute jobs, and also driving front-end applications out of data that's sitting in one of many cloud object stores. We see Array Lake as sitting in the middle, functioning as the central source of truth for your organization's cloud data. And it helps give you this kind of cloud native open source data access API through Zarr, as support for all array data file formats, so netcdf, HDF, and GRIB. And the key thing about Array Lake is that it solves a lot of the challenges that all of us experienced building production-grade data pipelines and trying to push the frontier of data-intensive research in our previous jobs. So for example, it provides a data catalog that lets you and your team easily find out what's available in your cloud data stores. It gives you search with metadata so you can find what you want, access controls if you need them, transactions, so the ability to safely modify the data in that object store. This is something that will be very relevant to what I'm going to show. And also data versioning, so you can easily move, view different versions of that data set and always be sure about which version is being used for your downstream application. A lot of what I show is going to be owes a lot to a lot of people around the world for a lot of infrastructure and code that they've shared freely. So thanks to the NOAA Big Data program for putting a lot of weather forecast data in the cloud. This demo is going to use AWS, so thanks to AWS for making all of that data available for free through the Open Data program. Strong shout out to Brian Blaylock for this package called Herbie, which lets you find forecast data to a variety of cloud providers, as well as FTP servers, which is great. ECMWF and the surrounding GRIB ecosystem, which is very invaluable. Also, thanks to many members of the PlanGeo community for working on Zarr, Xarray, and many discussions on analysis-ready forecast data over the years. So rough outline for the talk. And I'll dive into this for the rest of this half hour. What I want is the ability to pull out a fast query to get a forecast at a single point. So I just want the next 18 hours of data at a single point. The way I'm going to accomplish this need is to build a pipeline that automatically transforms forecast data sets from GRIB files in the cloud to a cloud-optimized Zarr data cube. I built a data pipeline to do this transformation regularly because the forecasts come out at a regular frequency. I'm going to explore serverless execution in the cloud. So this is just an automated job that's going to continuously do this transformation for me as a new forecast lands in the cloud. The code that I use to do this is up online. So you should be able to see that. And you should feel free to take it and adapt it to your needs. And part of this talk is to just document the learnings and challenges I faced and learned while doing this, in the hope of making it more accessible to more people, because we've been talking to a lot of people who want to do something like this. Who is doing this today? We found that there are many heavy users of weather forecast data. This includes companies like energy grid suppliers and operators, energy market traders, hedge funds, supply chain companies, commodities traders, as well as academic and nonprofit researchers, right? So this is a common need that we've kind of synthesized across many conversations. And what we're going to do in this webinar today is to simplify the problem down to focus on the data pipeline, because that's the challenge we hear a lot from the people working with this. As a rough motivation, I'm going to use the problem of solar energy forecasting. So I've learned that weather forecast data is commonly used for a kind of 6 hours in the future to a day ahead projection of how much power might be produced by your solar assets. This is kind of personally very interesting to me because I have solar panels on my roof. And so I was kind of interested in how well could you predict that using forecast data. But I'm going to simplify this really a lot. And as a stand-in problem for some kind of complicated forecasting or regression problem, I'm going to instead make it more of a verification thing. So all I'm going to do is pull out the latest weather forecast at a single point, and I compare that to a very high-quality baseline measurement. So this little figure is what illustrates the kind of query that I'm interested in. It shows the last 3 days of forecast for a station in Seattle. The x-axis is the forecast time. The vertical black line is today, right now, in UTC. And so these are the forecasts for the last 3 days. The y-axis is global horizontal incidence. So this is the incoming solar radiation from the sun. Max value is something like 1,000 to 1,400 watts per meter square. You'll see a number of lines. Each line is a different forecast for that time. And so darker colors means a forecast that was initialized closer to the time that you're looking at. So as you go from light colors to dark colors, you're moving from an older to a more recent forecast. And you can see this tends to be a bunch of spread, right? And so my stand-in for a more complicated problem is going to be just a comparison to a very high quality baseline measurement from NOAA's SolRad network. So there's a network of 10 stations around the country that have very, very high quality sensors. And so that red line is a ground truth, very high quality measurement. You can see that the forecast is maybe not doing the best at comparing to a station in Seattle. And so the goal is to build up to this kind of figure for this demo, but just keep in mind that this is a stand-in for a more realistic application, such as transforming these forecasts into a power output projection or something like that. The forecast model I'll work with is HER, or the High Resolution Rapid Refresh model from NOAA. This is a 3-kilometer resolution model. It's updated hourly and is pretty complicated and fascinating. The domain I'll work with is shown on the right. So this is over the continental US. This is a map of the total cloud cover. The peculiarity of HER is that it runs every 6 hours. They run it forward for 48 hours. And every other hour, they run it for 18 hours into the future. Right? So sometimes you get a much longer forecast, and most of the time you get a shorter 18-hour forecast. And the grid shape, just for reference, is something like 1,800 by 1,100 points in X and Y. So how is that data distributed? And so our inside joke is that this is a stack of pancakes. And here's why it's like that. The data come out for a single model run initialized on the hour. The data come out as a bunch of GRIB files. So GRIB stands for gridded binary. It is the standard meteorological data format. And you get one file per forecast time step per model run. So every hour, you get a stack of files dumped into a cloud bucket. Each file is about 500 megabytes, and it has very many variables in them. And for each variable, what you get in one file is the spatial map. So you get all XY points in a single file. And so for each model run, you're going to get either 19 or 49 files. And so we think of that as stacking on top of each other in the step dimension. So that's the forecast time step. And so that's why we think of it as a stack of pancakes being delivered into your cloud bucket. And so the query that I want to make is that I want to pull out the values at a single point to make that figure. And so you could think of that as opening each file, extracting the value at a single point, and then assembling all of that together to make a nice little time series. And so all of this data comes in a cloud bucket. And so I come with an oceanography background. This is my first real exploration of the forecast data sets. And it was interesting because I was just clicked through to this nice little cloud bucket that has all this data. It has a folder per date. And so once you click into that, you get a large list of files. And then you have to start interpreting them, right? So the date up here, so these are the forecasts for 2024, May 12th. T00Z means this is the run that was initialized at midnight UTC for that date. And then the data comes out in these .grip2 files with F09 means the 9th step into the future. And so the grip2 actually has the array data, and there's an associated IDX file that has metadata about the data. And this is all, it's not very clear. Right? Where is the data? What variables are available? You could click through this metadata file, but then you find variable names that have only 4 characters. And it's kind of hard to understand and really get a sense of how you would work with this, right? And this is the kind of challenge we've heard a lot of people tell us about. Like, the data are public and open, but it's a little hard to work with, right? And it's not that different from my supercomputing experience when I was a grad student and I was just pointed to folders that had thousands and thousands of NetPDF files, and I had to make sense of them to understand how to actually do research. And so what do we want? What we want is a data cube, which is more analysis ready and cloud optimized. And so the reason I think of a data cube is because it's the natural organization of the data in some sense. So you could think of this little stack of pancakes that's come out sliced up individually. And you could instead think of this as a three-dimensional array. There's a latitude, longitude, and a step dimension. You could think of stacking these cubes up along another dimension called time for each model run. And so then you'll end up with this 3-dimensional to 5-dimensional cube, depending on how many dimensions your input variables have. And so our goal is to transform the stack of pancakes to a cube that is cut up into little columns. And so the nice thing about such columns is that when you pull out a single time series, it's pretty fast. It's just a single request, hey, give me that column, and I can make my plot, and it works really well. So this is why it's analysis ready. This particular cube that I'm going to build is going to be optimized for the analysis I want to do, which is to pull out a single time series and then go on and do something else with it. We picked this problem because we know we've talked to many people who are doing something like that, and they're doing transformations like these in the cloud. Not everyone is doing this, but a lot of people are. And the reason they're doing it is because once you have the cube, this kind of query ends up being about 7x faster than doing the same query with your stack of pancakes, which is how the data comes out, right? So if you go to the native grip files, it's about 7x slower to do that. And sometimes that's quite important, particularly in kind of machine learning contexts. Okay, and so the goal of this webinar is to kind of communicate how I went from this stack of files sitting on AWS that's hard to navigate to a nice little cloud native data cube on Array Lake. And I'm going to switch over to this little dashboard here. And so if you sign up for Array Lake, it's organized into teams called organizations. And so I've ingested this data to an organization called Earthmover Demos. This is my activity over the last month. So you can see about 2 weeks ago, I started cranking on this problem and slowly started ingesting more and more data at the time. So it's trending upwards. The x-axis is date. The y-axis is number of bytes stored in this organization. On this side, you'll see a more nuanced breakdown of that activity. It splits it up into reads and writes. And so you can kind of tell there are certain days, this day in particular, I iterated a lot on this pipeline and just kept repeatedly writing. And so you can see that pop up. And you can also see a day that I just threw a big job at it just to test the limits of this pipeline. And I took in about close to 1 terabyte of data, and it all worked pretty well. Here's another view of my activity over the last month. This is the number of commits or number of updates to these data sets. So you could see as I was iterating on it, I kept committing more or updating the data set more and more. And then over the last week, it's kind of stabilized, and the pipeline's just been running smoothly in general. So now I'm going to click through. So once you click in, here are a bunch of repositories. And I'm going to click into the her one, which is the subject of this webinar. So you should think of a repository as a Zarr store. It's got a bunch of groups in it. In this one, I have one group called Solar, because I'm kind of coming at it from a solar forecasting point of view. One of the questions I had with all the data, all of those grip files, was what variables are available and what's not. So I can click through. I see there are about 10 arrays here. They still have these 4 or 5 character names. DSWRF, familiar to people in the field, not very familiar to people outside it. But the nice thing about Array Lake is it also surfaces all the metadata. So this is downward shortwave radiation flux, so incoming solar radiation. This array has 4 dimensions. X and Y are the 2 spatial dimensions. There's a time dimension, which is the one time dimension for each model run, and the step dimension into the future that has size 49, right? Remember, the model runs at most for 48 time steps plus initialization, so 49. I've ingested 237 model runs so far, and then for the whole continental US grid. This array is cut up into nice little columns as illustrated. So in this case, I chose to cut it up into this little chunk shape where there's 19 steps along the step dimension. And so that just works very well with this her output where the shortest forecast is 18 hours in the future. And that's kind of what I'm interested in. Array Lake also surfaces all of this nice metadata about the data sets, in particular things like the name, which we saw, downward shortwave radiation flux, and also the units, right? So all kinds of important metadata is available and very quickly to access. So it'd be a lot harder to find if you were trying to dig through those grip files in the cloud. Last thing I'll show is you see this data set has been updated 194 times. And you can see that it's been updated every hour on the hour, increasingly. And it's been driven by this little automated pipeline that's running in the cloud. And I've dumped in some information about what write was committed. We can talk about that later. And so you can see this has been running for a while. So I've made close to 200 updates to this data set. And so once I have this cube, what do I do with it? So here's how I'm going to interact with it. This is a little Jupyter notebook. And so I've opened this little repo with Array Lake, and I look at it in this tree view, which is very similar to that app, the view in the app that I showed you. So there's all of these arrays that I can access. I'm going to convert this to a little Xarray data set, which hopefully you're familiar with. If you're not, Xarray datasets have data variables. So these are the nice little arrays with all of that metadata. So DSWRF is the shortwave radiation, and associated coordinate arrays, latitude, longitude, step, time, all of that. So this is what Xarray really lets you bring along all the metadata that's associated with your data, and that makes life quite easy. For my super simple stand-in problem, I'm going to look at what's called global horizontal radiation. To build up this variable, what happens is that forecast models usually save the clear sky irradiance. That's that little DSWRF thing. And you need to account for cloud cover, which has also been ingested as this TCC little variable. I'm going to combine them just using a simple formula from this little reference. And so I'm going to show you that quantity. I'm going to first pull out the latest forecast at a single point. So I'm going to pull, this is the latest one. You've gone from 4 dimensions to 3 because you just picked out the last model run. I'm going to sub-select to my location in golden and look at my forecast. Like I said, the maximum incident solar radiation is something like 12 or 1300 watts per meter square. This is pretty typical for this time of the year, about a little more than 1000 watts per meter square. You can see that it's a pretty sunny day, which is totally right. It is bright and sunny and golden, but then later this afternoon, we are going to get a thunderstorm. And so the amount of incident radiation decreases, right? And so you could think of some way to go from this thing to the amount of solar power that my panels are going to produce. They're clearly not going to produce much later this afternoon, which means I'm going to be pulling power from the grid. Different way to look at the data, which is nice at Data Cube, is that we can look at nice little maps. And so I'm going to load and render a nice little map here of cloud cover. And so white means clouds, blue means clear sky. And then as you come in, you'll see I live somewhere down there. And you'll see little clouds come in as the day progresses. So data cubes are cool. You can work with them in many different ways. I'm interested in comparing to these baseline measurements, which I've already loaded. You can see, again, here's the little time series that I was trying to build up to. In selecting that data out is fairly simple with Xarray. I've just asked for the last 3 days of forecasts. I pick only every third forecast a day just to reduce the number of lines on the plot. And I've only asked for 18 hours of forecasts. And so I could do that at Seattle. Like I said, the model is okay. It's a bit problematic to get the clouds over Seattle. It does a lot better over Albuquerque, where you get to see a lot of sunny days. So if anyone's in Albuquerque, today looks pretty sunny for you, and it was pretty sunny yesterday. Seems to be some clouds and some uncertainty in the forecast yesterday. So here's a cube. It lets you interact with it in very many different ways. I've made simple plots as a stand-in for a more complicated application. So how was this cube built? To do that, we have to first look at how the data come out. And so here's a visualization of this herd forecast. The x-axis is the forecast initialization time. So if you go vertically, that's a single model run. The y-axis is the forecast time into the future, right? And so you started here, and you run the model, vertically, and it gives you output. The field I'm showing you is this solar radiation, so that's kind of nice. So you can see where sunrise and sunset are, right? What's daytime, what's nighttime. And the current time now is this horizontal black line. And so as you move horizontally, those are all the forecasts for this particular time that are available. And so you can see the data are kind of sparse, but you can still kind of work with them nicely once I've organized them into this nice little cube. And so for the next 5-10 minutes, we're just going to talk about how I assembled this cube and all the challenges that I ran into doing that. Right. And so one of the things I pointed out is if you look at this stuff on AWS, it's very hard to understand what variables are available. But once you get into this more cloud-native way of working with a Zarr store and a cube, suddenly, and a product like ArrayLake, you get all exposed. It exposes all of this metadata, right? And that's what you need as a human being to understand what's in those files. And it's very, very nice. So how did we get here? We built a cube that's optimized for these time queries at a particular location. This has many applications. So how did I do this? So the kind of algorithm or the flowchart is that a job gets triggered. It searches for the latest grip files in this cloud bucket. And then it asks, is there a new update since the last update to the array? If there's not, then you just exit and all's fine. It will just run an hour in the future. But there is almost always a new update. And so the first thing it does is it opens the Zarr store and resizes it to say that, hey, I'm going to give you another new time step. So please resize the Zarr array. Then it spawns a bunch of parallel writes. I'll talk about orchestrating this next. But you think of a bunch of parallel writes. Each of these is responsible for writing a section of the update. So all of that runs. If it's successful, then with ArrayLake, we commit and we seal our transaction and say, I'm good, and everything's great. What happens with these kinds of pipelines is sometimes they're not successful. The data wasn't fully written. The job was triggered just a little early, so not all the files are available. And so a couple of these tasks fail for this and that reason. And then what happens is the pipeline just aborts. And that's kind of where ArrayLake's transactions really started helping me. So if you remember, there was this day that I iterated a lot. And so there were a lot of aborts. And if you didn't have ArrayLake and you didn't have all these transactions, the issue is that you've resized the array. So you've told Zarr that to change itself, but then you haven't actually finished writing all the new data. So your Zarr store is in a bit of an inconsistent state, and it's not very nice for any downstream application that's trying to read the latest data. It's just going to get a bunch of nans, and that's kind of problematic. And so the nice thing with transactions is you can only seal your transaction. You can choose to seal your transaction when the pipeline is successful, and this means that the data in that store is always up to date and nice. And you don't have this issue of your downstream pipeline reading bad data. And so one of the challenges was navigating, this dump of files on a cloud store. Cloud store. I'd like to make a big shout out to this package called Herbie, which really simplified my life. It knows where to find a large number of forecast models on the cloud. It gives you a way to search through these for just the variables that you need. It knows how to interpret these IDX files or the metadata to just download the subsets of the grip file that you need. So if you're only ingesting a single array, you don't have to download all 500 megabytes of data. You can download 3. And that was a big speed up in the pipeline. It also helps you find what the most latest update is. So this was a key piece of the pipeline that I built. Here's a deeper dive into what it looks like. So Noah puts a bunch of grip files on AWS. Again, we've been thinking of these as stacks of pancakes. And so what I'm going to do is divide this whole stack into 3. Semi-arbitrary choice. Each worker is responsible for its own stack of pancakes. Each worker is going to use Herbie to read those into memory, assemble them up together, and then we use a combination of X-ray and Zarr to write to our Zarr target store. So in this case, that's ArrayLake, right? And so this is how I chose to parallelize it. So each one takes a stack of pancakes, concatenates it together into memory, and writes a subset of the output. And so once all of these writes are successful and no errors were encountered, I'm going to say, commit, I'm all done, and the data is good to update. And so that's what builds up that history of 200 commits that I showed you, right? So this pipeline kept running. It was, in general, pretty successful. And so every time it was successful, I sealed the transaction, and the data became available for any application that I want to use it for. So this parallelism was important. And so that little schematic showed you how I cut it up by time steps, right? So at most 49 time steps available. I process 19 at a time. You could totally do this another way, which is to just process a single array at a time. And you can stack all 49 at one go. So each task in that sense is responsible for a separate variable. And so this little bit of code that I've put up lets you choose one of these two options, depending on what's more appropriate for your use case. The way this pipeline was executed was what's called serverless computing, also called batch computing. It's good for these embarrassingly parallel data pipelines. So the way the pipeline was illustrated to you, each worker was responsible for its set of data and then its set of output. They don't talk to each other, right? And so it's kind of embarrassingly parallel and a little easier to manage. And so this is what's called serverless computing nowadays. There's no state to manage, no clusters. It's great for scaling out and using the full power of the cloud. The platform that I used was a thing called Modal, which is a semi-arbitrary choice. It lets you run a little scheduled cron job and was fairly easy to work with. Here's a little snippet of my cloud function. There's two of them. One's called backfill. This will just ingest a bunch of days. So this, for example, ingests from the forecast from 3 days ago till about a day and a half ago. And then the pipeline that I described a little more in detail was this update pipeline, which is just a single line that is being driven by a configuration file in the TOML format that I'll show you next. So it's just these little two functions that are running and that I use to build up that data set. There's a lot more code that's behind this, and all of that is public, and you should be able to take it and adapt it to what you need. I use Modal. There are many alternatives, Apache Airflow, Coil, LitOps, and I'm sure a whole bunch more. So it should be easy to adapt to whichever one you prefer. Yeah, so the example application should be up on GitHub. It's driven by this little TOML file, so there's a little excerpt here. The TOML file tells you has you specify what the inputs are. So this is whatever Herbie needs to find the data set. So that includes models names. I've added support for HER and GFS, which is the global forecast system, another pretty common product. Product tells you which set of files to look at. These are kind of Herbie specific or model specific, so that's something you just have to iterate on a bit. To choose the variables you want from the hundreds that are available, there's this little regular expression that you can write to build this up. There's more documentation up at that repo. So those are inputs. Then you tell it what the outputs are. You tell it which Zarr store to write to. I've been writing to Array Lake. You could make this any S3 Zarr store that works for you. And then you can tell it to write to a specific group within that store. So I showed you the Solar group. And the last piece of configuration is the chunking, or how you want to cut up your data cube. So this is the one that I showed you, where I chose to put 19 time steps in a chunk, because that was the shortest forecast that I would get from her. What did I learn? Using serverless was great. 2 days ago, I tested out the scaling by just ingesting a year of GFS forecast for a single variable. That was a terabyte. It ran in about 20 minutes, and I did no tuning. There were some failures. The retries were enough to have it all succeed. So that's, yeah. Ooh, I got the wrong figure. But there's a day when I ingested about 800 gigabytes in 20 minutes, and it was awesome. Managing the execution environment was a bit painful. There is some pain around CF grid and EC codes and all of that, but eventually I figured that out. Debugging was quite nice with Modal. So there's that day that I iterated quite a bit on the pipeline, and I had a good time dropping into an interactive prompt on a remote worker, and it was quite nice. There were definitely failures. So here's a little log where, for some reason, there was a failure, then a success, then a failure, then a success. So this is where Array Lake's transaction system really helped me, because anytime it fails, remember, we've modified the Zarr store by telling it to resize, but then we couldn't write all the data that we wanted to write for whatever reason. And so in this case, because I had Array Lake as a little safety net, I could just abort. Zarr store is always fine. And then on the next run, the one that succeeds, it's going to discover that, oh, I actually have 2 time steps I can ingest now, because the previous one seems to not have been written. So we'll just go and get that on the next try. And so it worked pretty nicely. And it's like a key reason the pipeline's been fairly successful the last week. So even if it fails, it's not that bad. It'll just update an hour later. So yeah, Array Lake is really like a layer on top of Zarr. And so it adds a lot of things to Zarr. So you still get, if you had Zarr, you just plain Zarr, you still get all the good integration with Xarray and cloud native stuff, but you don't get things like transactions that really help you, this kind of automated pipeline that's always running. It was very useful to have the version control and rollbacks when I was struggling and iterating on the pipeline. And the data catalog just makes everything just a lot more accessible. So what have we learned? The data cube model. it's nice. It was nice to be able to manipulate things any which way I wanted. But it also means that you have to make a choice. For example, I made the choice to optimize for this time series query at a point, and that required some kind of reorganization of the input data. That's just fundamental to data cubes today. This is a problem we're thinking about very hard, of how can we get away without having to reorganize the data this drastically. But so hopefully we'll have something to share with you later this year. Backfilling is kind of hard. So what I mean is, anytime an update comes in, it's easy because you can stick, a new little update on one side of the array, and Zarr makes that very easy. It's harder, for example, if you wanted to add a year of data, say, at the beginning of the array. And so when I've done that, what I did was try to use one group per year of data or something like that. So don't really use the cube, but then use a different hierarchical group type organization. And so that's a little hard. And one of the things we're thinking about is how to teach Zarr how to do more complicated inserts and insert at the beginning of the array instead of just appending to the end of the array. And then finally, here's my forecast. It's sunny, and then it's going to be rainy. And so, but this kind of query was pretty fast and quick to execute. And so that's why we're seeing many people choosing this pattern. They're choosing to make a copy that's optimized for time series queries in the cloud. And this webinar was an excuse to explore that pattern and tell you about what challenges that we ran into and how we chose to solve them. So with that, I'll end, and I'm happy to take any questions or discussion. Thank you for listening.
All right. So we'd love to do some Q&A here. It would be great if folks could submit questions through the Q&A panel that you should have access to over on the right. There are no questions in there right now, just a question about the public visibility of the code. We fixed that right away on the fly. And a comment from Brian, yay for Herbie. I think I did see maybe someone raise a hand. I'm looking for that.
Yeah, shout out to Brian again for Herbie. That was so awesome.
Okay, yeah, Riley, great. Why don't you go ahead and ask your question, Riley?
Hey guys, thanks Deepak. That was awesome. Always love seeing what you guys are doing, thinking about the hard stuff like storage. Love everything you showed here. Incredible. I'm particularly excited about what you hinted at the end, and I talked very briefly over email with Joe about this idea of thinking about how to chunk arrays more seamlessly. And just curious if you have any initial thoughts there, because it's like obviously perpetually a deep-rooted problem working with this data where you have to choose between a full-time, a full space, or a hybrid chunk scheme, and you're always like trading off regridding or quantiling or visualizing. Just curious, like initial thoughts you guys have about how to solve this problem without just having replicated data stores one kind of space chunked and one time chunked.
Yeah, nothing really to share there at the moment. We have some very rough ideas that we're exploring, but yeah, you're just gonna have to wait.
Okay, wasn't sure if you have any thoughts yet. I was very excited to hear about that.
It's pretty relevant for the forecast problem. So I optimize for a query into the future, but like the query into the past, say if you just wanted the last 3, 4, or 4 days, it's not as optimized as it could be. And so that's like a little angle that I couldn't explore. I just ran out of time. But that's one of these. It's definitely very relevant to this forecast demo, but I have no special ideas at the moment.
Cool, thank you.
I mean, it's a problem we're working deeply on at Earthmover right now, Riley, as I think you know, and we will be giving an update when we're a little bit farther along with something to share there.
Awesome, yeah, I'm looking forward to it. Hoping to chat with you guys soon about it.
Cool. All right. Well, we got a question from Jacob. Do we get access to the data, or do we have to work on your ecosystem? And further, can we take the data out, I guess, out of the environment? So Deepak, maybe you want to talk about, how people can run this without using Array Lake.
Yep. And so the idea with this thing was it was an exploration on how you could build this on your own. And so the little GitHub repository that was made public, you should be able to run that as long as you sign up for this modal thing, just because I chose to build it there. You should also be able to adapt this to run on with any service or orchestration platform that you like. And so I guess the short answer is the way you work with this today is to build your own cube. And we've tried to give you the tools that will get you very far down that path. So hopefully that answers your question.
We have an anonymous question here. What is the technology under the hood? Do you have a bunch of servers that support this? I'm not quite sure I understand what you're asking, anonymous. Maybe you want to just speak up and share your question a little more verbosely.
Yeah, not quite clear what that's referring to. But if it's about the pipeline, then it's built a lot on these open source packages. And like I said, the code's public, so you should be able to reproduce this. And there's no bunch of servers that are supporting the automated ingest that's running to this platform called Modal that manages all of that for you. When the job is run, it spins up a bunch of things that run these tasks, and then everything is torn down.
Any other questions or comments from the audience here? And we got one posted in the Q&A. Feel free to also raise your hands. Don't be shy if you want to speak up here. It looks like we've got plenty of time. So Michael asking, how do you load Grib per se? Is that a driver of its own? What library supports that? Yeah, Deepak, we'd love to get your take on this.
How do you load Grib per se? I think there's this thing called CF-Grib that plugs into Xarray, and that's generally pretty good. There is a newer package called Gribberish that's built on Rust that I've played around a little bit with, but it didn't end up using in this demo. So that's at least two ways that you can load a Grib file into a nice little Xarray data set. Now that you have the pipeline up and running, what's the approximate cost per day to maintain it? If you're talking about maintenance, sorry, this is a question from Christian Saracen. Maintain it. So I'm thinking in terms of like developer time. This is run for the last week or so without any intervention from me. So it was like about a week for me to spin up on forecast data sets and figure out how to wire it all together and get a nice little output. And since then, it's just been going. In terms of
I was actually thinking more along the lines of what was for the serverless jobs, what was your AWS bill? Just for like a week of doing this prototype, was that like $100, $10?
$12.
$12. Okay, great. I said approximate, right? So
that's what all of this costs total, I believe.
Yeah. Okay, that's awesome.
Really, that was $12 for all 2 weeks.
I think so. Let me try and look at some logs here.
Ryan has the power to pull up these numbers. I'll note that on the modal side, it was like $1 every 2 days or something. So it's that plus AWS. So
I guess that's always one of my paranoias about trying to explore some of these technologies. Like, I don't want to get like, oh, I'm going to let this thing go, and like, oh God, I'm going to have to pay for it. So $12 I can handle. 1,200 is a little different.
And I'll say I spend almost no effort trying to optimize for runtime.
Yeah, no, that's
none of it.
I figured.
So you could probably go lower.
Yeah, it's a super. I look for it. I'm gonna check out your notebook and start playing around. It's really cool. Thanks.
Deepak, on that note, is there, you named, there's Airflow, there's Prefect, there's Modal. We're using Kedro, and we're kind of sledgehammering it and looking for other options. I'm curious if there's been any workflow orchestration packages in particular that you think sing nicely with the Panteo ecosystem and Coiled and Earthmover. because some of these things like Kedro that we use here, because it's developed by Quantum Black, is really good for ML workloads, but not really meant to like orchestrate a bunch of different gridded array downloading, publishing, and stuff. So curious what you've come across as like good workflow managers for our ecosystem.
My experience has only been with Modal in this case for this kind of serverless thing, and that worked quite nicely. I had a good time, but I also don't have anything else to compare it to. But Ryan, in the previous demo, did work with a bunch of serverless frameworks. I'm going to punt to him here.
Yeah, I think we should distinguish between like the serverless runtime and like the more the orchestration. You're kind of getting a little bit of both here using Modal's cron jobs, but those could be separate, right? So you could use an orchestration framework like Airflow that has a nightly job that then triggers all of these serverless, functions to get called, or do that as part of a pipeline. And I think that's something I like. As you probably know, Riley, we've worked on Pangeo Forge for quite a while. We have a lot of experience with Beam. And I think where I've evolved is just try and keep it as simple and embarrassingly parallel as possible. So just, that's kind of how we've gravitated on these pipelines, just as much as possible, turn it into something with not a lot of sort of interdependencies between tasks or complex flow logic. And then it really kind of becomes a lot more like that old school HPC style workflow. Just launch a bunch of batch jobs from the cron job or something like that, which is simple, but kind of tends to work and get the job done. So in that context, you could use this approach of serverless computing with any of the things you just mentioned, because the data is not actually then flowing through that system. It's being triggered to move around in the serverless runtime. Does that make sense?
Totally. Yeah, no, I appreciate you guys. I don't mean to derail this. I appreciate it. Something we can probably talk about in another call, but that's super helpful. There's a lot of ways to do this, and I agree with you. Like you end up building up technical debt with the platform that you inherit at a company, and I think there's a lot of these simple things that don't have so many dependencies. And like you said, I'm just looking for a way to trigger it, like we're on Cheyenne or Casper or an HPC cluster where we can just quickly launch a named job and let it run through some workflow.
And probably also worth shouting out Coiled. If you're already a Dask shop, Coiled has serverless Coiled functions that work in very much the same way and offer like a similarly simple developer experience. So that's a good option to consider.
Yeah, we're just doing some initial work there, and totally agree. Seems like a nice thing to stack with Earthmover as well, just to kind of simplify all aspects of this space.
See, we got a few more questions in the chat. Can this approach be deployed on premise, or should one use external cloud? Deepak, do you have thoughts on that?
I think some version of this could be deployed on-prem, right? It's pretty simple in that it cuts up the problem into these independent tasks. As long as you have a way to run those tasks and you have a way to access the grip files on AWS, you could ingest to an on-prem system. Do you have anything to add there, Ryan?
What makes this work though and scale is the high bandwidth between the storage and the compute environment, right?
Yeah,
and so
good.
the data, the original grip data are in AWS and S3. And someone, by the way, mentioned object store. Yes, by object store, we're talking about S3 here, AWS S3. So the original grip data are in S3. The Zarr data we're building are in S3. And then the serverless runtime is also in the cloud, ideally in the same region as all the data. And so that's what makes it be able to scale out really well. Now, you could run those functions somewhere else. You could run them on your laptop for that matter. But they wouldn't be able to scale out as quickly and spawn as many concurrent workers or tasks at the same time. And then B, you would be limited by the network bandwidth between where the data are stored and where you're doing the compute. And so in principle, this can be run on-prem, but in practice, you're not going to get as good of performance and scalability unless you're really data proximate to the data. Okay, Nick has got a question here. How often are metadata DB updated when, say, grid tables change for new experimental variables? Nick, do you want to just go on audio and ask this question out loud? Because I'm not sure I understand what you're saying here. Feel free to just unmute and speak up.
Yeah, and sorry, I had to drop for a little bit for another meeting. So if you answered this, I apologize. So with grid tables like her, like for example, a couple years ago, they included like a smoke variable that was brand new. It was in the experimental her for a while and then transitioned to the operational her. At that point, I assumed that like the database of metadata that you use is then outdated and you would have to rebuild that, or would you add to it? I'm just kind of curious kind of how you handle the changes in models as they version up.
So this particular webinar was about building the transformation pipeline, and it outsourced everything, all the complexities of Grib to Herbie and CF Grib and all of the other packages in the ecosystem. So I'm entirely relying on external packages to handle exactly what you're asking about.
Cool.
So,
Yeah.
Brian
probably has an answer to this one specifically.
I can give an answer to that. Each grid file has its own metadata file. So when you read a particular grid field, it has its own metadata that tells you where those variables are located in the file. And that's how Herbie works. So when they add like a new smoke field, and it's just the metadata says, hey, in this byte range in this file, there's a different file field there.
Okay, yeah, I may follow up with you after a bit, Brian, maybe separately. I have kind of further questions that aren't really relevant here.
Yeah, no problem. Send me an email.
Cool. All right. Well, we may be running out of questions here. Anyone have any final thoughts or questions they want to share before we wrap up? All right. Well, I want to thank everyone for coming out to this webinar. Our intention is to keep doing these on a monthly basis. If you have any requests for what you'd like the next webinar to be about, if there's a particular cloud data problem that you're wrestling with, don't hesitate to reach out to us. This will also be recorded, and so if you have colleagues who weren't able to make it, we'll be putting the video up on YouTube. So thanks to everyone, and especially thanks for Deepak for this really interesting talk.
Yeah, great. Thanks everyone for coming. This was fun. Take care.
Thanks, Deepak.